Hi everyone, this is an updated version of the A2 proof pack. So this is for 2025. There's only a few things changed in it, but there are a few little changes. So let's have a look. So first of all, this is now a starter, whereas it was something that you did outside of the lesson first, like a self-study bit. So it says, let's have a look at the important bits from this page. So it recaps the first year. So a convincing demonstration that your mathematical statement is necessarily true. Right, so we've got one by counter example. So if x is greater than y, then x squared is greater than y squared. I want to disprove this. So because it's a counter example one, I just want to sub some numbers in. So if you have a go, just sub a few numbers in, see if it works or fails. But once you've done that, hopefully you will get, bing, this. So if y is negative, when you square it, it's positive. So if you've chosen y as being a negative number, then it'll fail. And we've got a statement at the bottom here, haven't we? Including this part here. Right, so there's another one here, proof by deduction. So direct proof, logical algebraic steps, so I like a bit of algebra. So prove that n cubed minus n is a multiple of 6. So if it's a multiple of 6, I'm looking for it to be a multiple of 2 and a multiple of 3. So I'm kind of thinking here, 3 consecutive integers. That's what I'm thinking. We'll see if that works when we take the thing off. There. So I've factorized. It's not overly obvious here at the second step, but the third step is 3 consecutive integers. And if you think of any 3 consecutive integers, I don't know, 4, 5, 6, you've always got at least one multiple of 2, because there's 2 in there, and a multiple of 3. So if you've got a multiple of 2 and a multiple of 3, you must have a multiple of 6. So that's that one done. And then I've got proof by exhaustion. Oops, not dropping down enough. So check all the possibilities. So I'm told that it's between 2 and 20, and n can be written as a sum of 2 prime numbers. So let's have a look what this does. So n's going to be even between 2 and 20. So I'm looking at 4, 6, 8, 10, 12, 14, 16, 18. I want to prove it can be written as a sum of 2 primes. So 2 plus 2 is 4, 3 plus 3 is 6, 5 plus 3, 5 plus 5, 5 plus 7, a few alternatives for 14, 16, and 18. I've shown them all. Now, if you look, change to the highlighter. The question said there, and look, the answer says the same. So what's important there is that the answer has the question in it. So when you do your conclusion, you want to write the question into the conclusion. That's important now. Here we go, about Goldbach's conjecture. There. Right then, let's have a look. Seem to have lost the top of it. So I'm looking at proof by contradiction, which messes with your head a little bit when you start, but once we've done a few of them, it still messes with your head, to be fair. But by the time you get to the exam, it messes with your head less. It's the important bit. Right, so proof by contradiction then. So it says we need one further method, proof by contradiction. Assume that the negation of your statement is true. Hence, logically derive a contradiction, something which is clearly false. The assumption must have been false. The opposite of your statement, therefore, false. So your statement is true. So if you want to show something is true, what you want to do is show the negation is false. Show everything else is false. So if you want to show something's true, show everything else is false. That's what proof by contradiction is. Right then. So what's the negation? So the negation is when we say a conclusion is not true. So if P, then not Q. For each of the statements, write down the negation. So all cats are evil. So that must mean then the negation must mean that there is at least one cat that isn't evil. So at least it's not evil. There is no greatest even integer. So there is a greatest even integer. Why not? If n cubed is even, then n is even. So on these questions, it's this little bit at the end that I change. So if n cubed is even, then n is not even. So it's odd we're saying, aren't we? But it's nice to write it as not what it says in the question, because it links in with the question then. So then it says there are no positive integers m and n such that m squared minus n squared is equal to 6. So there are positive integers, because it's everything that isn't it. It's hard not to say the word opposite, but it's not opposite. It's everything that isn't it. There are positive Sorry, I'm using a new board. Well, to be fair, it's the first time I've written on the board or since the summer holidays. So my writing's bad enough as it is, but it's a new board as well, so it's a little bit all over the show. There, so there's some ones I've done. That's some questions for you. Hopefully you'll do these without just copying. But there's the answers that they've got. And I think that's the end of the first, is that the end of the first lesson? Or was that a quick exercise? Oh, no. It's just a quick exercise and wants to practice. So we'll keep on going. We're still on lesson 1. Sorry, everyone. Right, so let's have a look at these questions then. So it says, prove there is no greatest odd integer. So I want to assume that there is a greatest odd integer. So my contradiction, put it in a different column. Is assume call it n. All right then, so if it's odd, I'm going to take my number, n. If it's odd, it's made up of 2 lots of another integer plus 1, where k belongs to the integers. So if that's my greatest odd integer, if I just add 2 onto it, so that'll be 2k plus 3. But that could be, so actually, no, I'm going to rewrite that 2k plus 3. No, actually, do you know what? I'll leave it as that 2k plus 3. But now I'm going to rewrite it as 2k plus 2 plus 1, which is 2 lots of k plus 1 plus 1. And that's in the form of an odd number. So what I've done, if I assume that n is the greatest odd number, what I've done is find a larger odd number that's next to it. So my contradiction has failed. So n plus 2 is an odd number greater than n. So my contradiction has failed. Therefore, there is no greatest odd. So you've kind of got 3 bits to this. You've got the original part, you've got the contradiction, and then you've got the conclusion. So if you want to show that something is true, you show the contradiction is false. If you want to show that something is false, you show the contradiction is true. That's the idea behind it. There's one here for you, prove that no large is an even. So similar idea. There, similar setup. Set my contradiction up, work it all out, then I've got some form of conclusion to go with it. There. So different teachers might write it out ever so slightly differently, but same idea. So example 2 then, so prove that n is a positive integer and n squared is even, then n is even. Right, okay. So this last bit is what we want to change. So my contradiction, just write it in red so it stands out. Just so you know, really, you don't necessarily need to, you wouldn't write contradiction on the exam paper, but I'm just setting it so you can clearly see what it is. So assume if n is a positive integer and n squared is even, then n is not even. So it's odd. There. Right then, so that's my contradiction. That's the first little bit. So assume if n is a positive integer and n squared is even, if you can read my writing, then n is not even. Right. So if it's odd, let's set our odd number up. 2k plus 1, where k belongs to the integers. But before I could have negative numbers, to make this work, I just want to, like on this other one up here, when I said it was the integers, I could have positive and negative values. On this one, I just want to be a bit sneaky. I'm going to put a little plus here, so it's just the positive integers. So unless, 0 and the natural numbers, to be precise. Right, so let's have a look then. So it says, if n squared is even, then n is not odd. So n squared is even, so let's have a look at n squared then. So n squared is 2k plus 1 all squared. So n squared will be 4k squared plus 4k plus 1. Now, remember, an odd number is 2 lots of something plus 1. So I can see this as two lots of k squared plus 2k plus 1. So I've got two lots of something plus 1. So n squared is an odd number. So n squared is odd. So n squared, now if you think about this one now, I've shown that the contradiction is true. So the original statement must be confusing me. That's odd. Hang on, I've misread something. So n squared is odd, it contradicts the original statement. So if n is positive, look, n squared is even. Nah. So we wanted n squared as odd, getting all confused with me odds and evens here. So we wanted n squared even. So my contradiction has failed. I misread my evens and me not evens. So as n squared is odd, contradiction is false. Therefore, if n is a positive integer and n squared is even, then lots of n's there, then n is even there. Got myself like got myself confused. First day back, you know what I mean? So n squared was odd there, and we wanted that to be even. All right, so there's one there for you. There, same idea. I think we've got a couple more, and then we finish this lesson. Right, then, so let's have a look at example 4, it says, but I think there's an example 3. There is. Right, so it says, given that P and Q are integers, such that PQ is even, use algebra to prove by contradiction that at least one of P or Q is even. So P and Q are integers such that PQ is even. Use algebra to prove the contradiction that at least one of P or Q is even. Right. So what's the opposite of, oh, sorry, no, not the opposite. What's the negate of at least one of P or Q is even? And that is that both of them are not even. So the negation is that both are odd, that P and Q are odd. So I'm going to assume, so this is my contradiction, just write down a different colour so it stands out. Don't do it in the exam though, but it just helps you when you look back on your notes. So assume in the loop is even, comma. So appearance just such that PQ is even, P and Q are not even, so they're odd. Because at least is everything apart from none of them. And the negate is not the opposite, it's everything other than it. So assume P and Q are integers such that PQ is even and PQ are not even. Make it a bit thinner, see if that makes it better. Right then, so I'm saying that P and Q are odd. They're not consecutive, so they're not next to each other, so they get set up with different letters. So that was something from last year. I hate these new boards. They look really swishy, but they're really hard to write on. Right, so let's set P up then as 2n plus 1. Let's set Q up as 2n plus 1. There. M and N are integers. M and N belong to the integers. Right, so PQ, I've got to look at them times together. So PQ is going to be 4mn plus 2m plus 2n plus 1. So remember, I want to show that this is odd. So I want to do it as 2 lots of something plus 1. So I've got here that PQ is an odd number. So my assumption, so assume P and Q are integers such that PQ is even. So if you look, I was trying to show that PQ was even. But actually what I've shown is PQ is odd. So this is where my contradiction is. So my contradiction fails. Therefore, if P and Q are integers, such that PQ is even, comma, then at least one of P or Q is even there. So I had a contradiction that said, if P and Q are odd, see if PQ is even. And P and Q were odd, gave me PQ as odd. So my contradiction failed. And then I've got this, they've got the answer there. You see how messy this is? Show that something works by showing that the contradiction, the negation, doesn't. Right then, I think we've got one more and then a question for you, and then we're done for this lesson. So prove that for A, B being integers, there are no positive solutions to the equation a squared minus b squared is equal to 1. Right. So we want to see if there is a positive solution, don't we? So assume for A and B being integers, there is a positive solution. To the equation a squared minus b squared is 1. All right. God, how do we do this then? Let's have a look at a squared minus b squared is 1. Hopefully, it hopped out at you that that's a difference of 2 squares. So I've got a plus b and I've got a minus b. If a and b are integers, as I've scruffily written up there, then a plus b must be an integer and a minus b must be an integer. So that's one thing to think about. So as A and B belong to the integers, comma, A plus B and A minus B are also integers. Right then. Let's have a go at this one then. What if one of them was equal to 0? Well, no, actually, don't say that. Let's set A plus B to be 1 and A minus B to be 1. If we do that, which is a bit weird, this one, isn't it? It's the solutions to it. So I'm trying to solve this. So if I do that, I get A is 1, I get B is 0. So it says, though, that it's positive. 0 is not positive. So B is 0, it's not positive. Try it the other way around. So if I look to solve minus 1, should put plus there. It don't matter. Try solving that. Gives me that. And that's the same. These are both not positive. So my contradiction said that there was a positive solution. But if you look, my answers say different. So my contradiction fails. I don't like this question, but never mind. My contradiction fails. So if A and B belong to the integers, there are no there you go. So that was a little bit more messy. Sorry about that. We kind of solved it in the middle. I think you've got a question for you, and then there's questions there. So I'll put up the answers to this. I'll have a go with it. There you go. There. So that will this. Oh, this I think this is an exam question off a different exam board. So you can see that they've tried solving. And that previous example was one that was added, so I've never seen that before. And that's just kind of help us with this one. So you can see that the kind of like that their idea behind it is to say that 28 is 1 times 28. Or 7 times 4, that type of thing. So, right. I think we're done. You got some questions there, haven't you? Well done, everyone. Bye-bye.